Right now, your phone knows exactly where you are, within about 3 feet. Think about that for a second. A tiny device in your pocket is communicating with satellites flying 12,000 miles above your head, traveling at thousands of miles per hour, and it pinpoints your location with almost absurd precision. But here is what most people do not realize. That system, the global positioning system, would be completely useless without corrections based on Albert Einstein's theories of relativity, not metaphorically, not loosely. GPS literally proves Einstein right every single day, billions of times over. Let me explain how. To understand why Einstein matters to your morning commute, you first need to understand how GPS actually works. The system relies on a constellation of at least 24 satellites orbiting Earth. Each satellite carries an incredibly precise atomic clock and constantly broadcasts a signal that essentially says, "I am here," and the time is exactly this. Your phone picks up signals from at least 4 of these satellites simultaneously. By comparing the tiny differences in arrival time of each signal, your phone calculates how far you are from each satellite. With 4 distances, it can triangulate your exact position on Earth. Simple enough in theory. The signals themselves travel at the speed of light, roughly 186,000 miles per second. At that speed, even the tiniest timing error translates into a significant distance mistake. But here is where things get strange. The entire system depends on those clocks being perfectly synchronized. If the satellite clocks drift from the ground clocks by even a tiny amount, your position calculation goes wrong, and not by a little. A clock error of just 1 microsecond, that is 1/1,000,000th of a second, translates to a position error of about 1,000 feet. Now imagine those errors accumulating minute after minute, hour after hour. Within a single day, GPS would be off by miles. The system would be worthless for navigation. You would end up driving into a lake, or off a bridge, or past your exit for the 50th time, except this time it would not be your fault. So the clocks must stay synchronized, and this is exactly where Einstein enters the picture. Einstein published 2 revolutionary theories during his career. The first, special relativity, came in 1905. The second, general relativity, came in 1915. Both of them affect GPS, and they pull in opposite directions. Understanding each one separately is essential to seeing how they combine to create a problem that engineers must solve every single second. Let us start with special relativity. One of its most famous predictions is time dilation. When an object moves at high speed relative to you, its clock runs slower compared to yours. This is not some illusion or measurement error. Time itself genuinely passes more slowly for the moving object. GPS satellites orbit Earth at roughly 8,500 miles per hour. That is fast by human standards, but it is a tiny fraction of the speed of light. Still, it is fast enough for special relativity to matter. Because the satellites are moving relative to clocks on the ground, their onboard clocks tick slightly slower. How much slower? About 7 microseconds per day. That might sound insignificant, but remember, 1 microsecond equals 1,000 feet of position error. 7 microseconds per day would introduce roughly 7,000 feet of error daily. That is over a mile. Imagine your map telling you the restaurant is a mile away from where it actually is. Every day, the error growing worse. Now let us bring in general relativity. This theory says that gravity affects time. Specifically, clocks in a weaker gravitational field tick faster than clocks in a stronger gravitational field. Think of it this way. Down here on Earth's surface, gravity is relatively strong. Up where the GPS satellites orbit, about 12,000 miles high, gravity is weaker. So the satellite clocks actually tick faster than identical clocks on the ground. How much faster? About 45 microseconds per day. This effect is more than 6 times larger than the special relativity effect, and it goes in the opposite direction. So we have 2 competing effects. special relativity slows the satellite clocks by 7 microseconds per day. General relativity speeds them up by 45 microseconds per day. The net result? The satellite clocks run fast by about 38 microseconds every day compared to clocks on the ground. 38 microseconds might still sound trivial, but multiply that by the speed of light, and you get a position error of roughly 7 miles per day. Every single day, the errors would compound. Within a week, your GPS would be off by nearly 50 miles. The entire system would collapse into uselessness. This is why GPS engineers build relativistic corrections directly into the system. Before a GPS satellite is even launched, its onboard clock is deliberately set to tick at a slightly different rate than ground clocks. The frequency is adjusted to compensate for that 38 microsecond daily drift. The clock frequency is shifted from 10.23 MHz down by a tiny fraction, precisely calculated using Einstein's field equations. Once in orbit, additional corrections are applied in real time by ground control stations. The math behind these corrections comes directly from Einstein's equations, not approximately, not inspired by. Directly. And here is what makes this so remarkable. Einstein developed both of these theories decades before anyone dreamed of GPS. He was thinking about thought experiments involving trains and elevators and beams of light. He had no idea his work would one day be essential for helping people find the nearest coffee shop. Yet his predictions were so precise, so fundamentally correct about the nature of space and time, that engineers over 50 years later could use his exact formulas to make a global navigation system work. Let me put the precision in perspective. The atomic clocks on GPS satellites are accurate to about 1 nanosecond. That is 1/1000th of a second. To keep GPS working, the relativistic corrections must also be accurate to that level. This means Einstein's theories are being tested and confirmed to extraordinary precision every fraction of a second, every single day. It is one of the most rigorous, ongoing experimental confirmations of any scientific theory in history. No laboratory experiment has ever matched this scale of continuous, real-world verification. Some people think of relativity as abstract physics that only matters in extreme conditions, like near black holes or at nearly the speed of light. GPS proves that wrong. Relativity affects everyday technology. The speeds and gravity differences involved in GPS are modest by cosmic standards, yet the effects are large enough to completely break the system without correction. You do not need a particle accelerator to test Einstein. You just need a phone and a clear view of the sky. There is another fascinating detail worth mentioning. The GPS system actually tests both special and general relativity simultaneously and independently. Scientists have used GPS data to verify the specific predictions of each theory separately. The results match Einstein's predictions with astonishing accuracy. Some measurements have confirmed relativity to within 1 part in 10 billion. That is like measuring the distance from New York to Los Angeles and being accurate to within a fraction of an inch. Other satellite navigation systems work the same way. The European Galileo system, Russia's GLONASS, and China's Beidou all incorporate relativistic corrections. Every spacefaring nation that has built a satellite navigation system has independently confirmed that Einstein's theories are necessary and correct. This is not a matter of opinion or interpretation. It is engineering reality. Without relativity, none of these systems work. Each system was designed by different teams of engineers in different countries, using different satellite designs and orbital parameters, yet all of them arrived at the same conclusion. Einstein was right. Now, here is something to think about. GPS was first made available for civilian use in the 1980s. Since then, the system has been running continuously, making relativistic corrections every moment of every day. That is over 4 decades of non-stop experimental confirmation. Billions of position fixes per day, each one depending on Einstein being right. If his theories were even slightly wrong, the errors would have shown up long ago. They have not. The system keeps working, day after day, year after year. It is worth appreciating just how strange this situation really is. A man sitting in a patent office in 1905, imagining what would happen if he rode alongside a beam of light, developed mathematical descriptions of reality so accurate that they are essential for a technology he could not have imagined. His pure thought experiments, his abstract mathematics, his deep physical intuition about the universe, all of it translates directly into the practical functioning of a system used by billions of people every day. Every time you open a map on your phone, every time you follow turn-by-turn directions, every time a delivery drone finds its destination or an ambulance navigates to an emergency, Einstein's theories are quietly at work. The corrections are invisible to you. They happen silently, behind the scenes, baked into the very architecture of the system. But without them, nothing works. Your rideshare driver would never find you. Your fitness tracker would log your morning run somewhere in the next county. The entire modern infrastructure of location-based services would simply fall apart. So the next time someone tells you that theoretical physics has no practical applications, or that Einstein's work is just abstract science with no real-world impact, you can point to the phone in your pocket. The most widely used navigation technology in human history is living proof that Einstein was right. Not approximately right, not mostly right. Right down to the nanosecond. Every single day.